Well, I can't say enough about Jake Hebbert's reflections upon nature of code in Grasshopper, and if anybody does want to start learning Python programming, this is the way to do it, especially if you have modeling interest in Rhino and you have some practice in node geometries in Grasshopper. So what I'll do here is I'm going to close this one out for a second, the Python script. I'm going to stop this ball bouncing, turn that off, and we'll go back to the first script. I'll take off all of this, preview off. We will enable everything. And we'll go into the first script, and what happens is he basically has a Python node that he was feeding a timer into it. And maybe we should go back to that and show that timer. And I think it's all on preview on. So there we go. We have a sphere coming out of a Python node. And how is the Python node written in regards to time? Import Rhino syntax as rs. Set your x and y variables as constants, which is fine. You can set your x and y speeds, which are going to be used within this function, to 1. So you're initializing them to 1 and 3. You have an upper bound set to 90. This is off of a processing script in nature of code. There's no reason to have this here, even though I baked it in. For t in range time, you will basically be able to set your time value to, let's say, 260. It's going to loop through x equals x plus x speed, which is 1, and y is going to be y plus equals y plus y speed, which is 3. And then for for this, if x is less than 0 or greater than the upper bounds, which is set to 90, it's going to change direction. So the speed is going to multiply by x speed is going to multiply by x speed times -1. The same thing happens for the y speed. And then you simply output a Rhino script add sphere, and when you click on add sphere, it'll come up in the help line down here as to what you need. You'll need your x and your y, and there's no z on there, and it will move at speed 10. I believe it's speed 10. I'll just have to double check that. Let's run it on true. The timer, and actually the timer counter is going to be set here, and there we go. And there's a little bit that has to happen here that's pretty interesting. We'll go into it. Let me just take that time up to 30 and run it. Oh, it's scale. Sorry, it's the radius of the circle. I don't know why I thought it was time, because we're dealing with frames per second. So my mistake. Then again, logically, I make lots and lots of mistakes. So let's take this back down to 10, test it, and then let's see what else is happening in the script. As we close out the script, we basically, instead of the time coming in here, we wanted time to be this counter. So we reset it, and then we trigger it again, and your time counter is going up at 20 milliseconds. And you can reset that interval to, say, 50 milliseconds. And I think we might have to set the test again, but no, it's fine. And it's taking a picture every 50 milliseconds. So you can just keep changing that, playing with it. And what he shows is this efficiency of going through, having to iterate through all of this, and trying to move that around. You can set that to a really nice tool as the timer. I think it's a great example of what to do. So let's turn that off. Now efficiency says if you want the script to be efficient, you can actually use the list index, which is taking this number as we turn it on and setting that. And I'll put this all over. And actually we only want to view this one, the ball. We don't actually want to view the point coming out of the, I believe it's the untrimmed surface coming out of here, because it's still a sphere that's being generated, but we want to just see it as it hits this counter. And this speeds up the script quite a bit, that you can use this number slider again as 1,000 frames. You just don't want this to climb above your limit here. So let's take a look at what the script did differently. And what it did differently was it might be good if I pull this one up. You've got the original one here. This one's the second one. This one's the first one on the left. So basically going in and rewriting the script, they put in a list for the second one so they could actually append that list with the sphere and then send the list to the output, which is really going to make it more efficient than putting the add sphere right to the output. And then any changes that occurred in here, it looks like the only real change was adding that list, which is a technique we've used all the way back to as I close this and this is why I always leave this nice example up over here of a script basically producing a list, setting your loop, and I use a little bit of maths in here, but that's unimportant, naming your add point, appending it with that variable name internal to the function, and then sending that out to the output. So using this list way of doing things obviously is a much more efficient way to do it. You can see we just produced those that other piece again. Every time I run it, I produce those points. So if that's not making too much sense, we'll just bring up both scripts and have a look at what's happening there. Now what I do is I have another example of a 2D that right here, preview on. And you're not going to want to see all these points, so definitely I'm probably going to want to take this counter and put that to display off. And what happens here is the same script has been built. They do a couple of checks in here, which is interesting. I should bring up the past script to compare it to it. Let's bring this one up. So what's happened is the importing, they've then made a vector instead of points. So a positive vector of 50, 50, 0, and they show where those are being x, y, z, 0, 1, 2, but those are commented out now. You have your bounds the same. Your velocity is now set to velocity, and that's kind of unnecessary. You could have just called it velocity, but and printing velocity to see that vector, just as an example as the output, as opposed to the A. And then he sets up another T list, so it will move very fast. He's going to have the positive vector, instead of these points being produced every time, he's going to take the positive vector and name it after adding the vector, and it needs two attributes, which will be itself and this position. So the position is being named again, the vector is being added plus that other vector. So it's taking one vector, adding another one, adding another one, adding another one. So you just have to kind of wrap your head around that, and then back into the same system of making a variable to define the adding point in reference to that position, and then in reference to that vector, and change vector, I should say, and then the T list is appended by the sphere, and you send that out, and that will be a very fast moving script that's even more efficient because it's dealing with vectors and not these single points, and that will allow you to do more and more things and hopefully deal with more and more spheres, and you can have like really cool collisions and things like that bouncing off one another. Anyway, we should turn this one off, otherwise it'll keep running. That one I should turn off because it keeps running. And this one, if I set to true, you can see how that one is producing those spheres, and you can actually, they just made your sphere kind of pulled it out so you can actually play with that a little bit. So what's being pulled out of here is the point position is being pulled out, not producing a sphere, which is going to speed it up, the script up quite a bit, because it doesn't have to deal with that. Deal with it as a physical piece of geometry, and you can pull out those points, reference your points, and then put your spheres out afterwards. And at this point, if you really wanted to go fast, if you had a lot of them, you could always go into your mesh tool and pull up a mesh sphere, and it'll move a lot faster, obviously, than a NURB sphere. Okay, back into it. False to true. Shut this one down, and definitely take a look at all the videos and walk through all of these. These are just kind of highlights to it. Now, why is this script not working? Oh, because my point has been changed. What I'm going to do on here is take a point, and I'm going to place it in here, and I'm going to grab that point, I'm going to lift it up, and I'm going to set that point into this point that feeds into the vector. And there's a little thing that they show us here, that when you have a vector point like that, hang on, set one point, there we go. If you put this directly in, it'll bug out to the velocity, but if you run a point through a vector, and into here, and what I'm going to do is just, I'm not going to internalize that point as of yet, because I may want to gumball and move it around a little bit. So if I move that, I should be able to change the grasshopper. But what I need to do is make this, well, I could make it visible, but I think I'll just leave these visible preview on. There's our sphere that's informed by this point through that vector, and what's the script change to keep going with this system as that wants to move. As that sphere, what we've done, or what they've done, I should say, is opening the script. You'll see what they've done is they've set up the vector the same. They have the bounds, they still have the velocity, they print the velocity, they did a list, but as they go into here, they've decided to add a position vector 2, which will reference the z. And so you've got 0 referencing x, 1, 1, 1 referencing y, and z, z, z referencing z. And now you're bouncing around an actual box. And they continue through having an output a point that you then can put through a list item and put into a sphere. And you can change and modify that outside of that with more nodes. So I think Python is actually learning the technique of using the Python script for what you can to make a very fast script, and then bring that out and network that with a node system in Grasshopper that makes sense to you and your basic and intermediate understanding of it. Hopefully that makes sense. And then what they do here is the same thing, and I'm just going to grab that point, and actually the positions of these points. I'm actually going to internalize this sphere, but if I move this point and it references that point, I will say that the sphere will speed up and slow down depending on the size of that vector and how far away that point is from its origins. So let's turn this one on. You can see there's the point path, which is kind of good to think about for robotics, because that's really the position of where this is going to mill and move. So if you start connecting this technology and this digital work with the paths of robotic paths, you're really starting to make some leaps and bounds, I think, conceptually, as to what's really happening here. I'm going to take this and ungroup. Oh, it's so hard to ungroup. There we go. And we follow the same point, even though I pulled it from up here because I was just being lazy. Put it into velocity. I have the time. What's the real change on this one? It's very subtle. It's very small. We'll close that one. The real change is they just put another for loop in of for I in range 3. They can let that position change from 0, 1, 2 instead of having to write this 3 times for X, Y, and Z reference to where it is. So that's a really nice use of that script playing off of this script, and you can see the subtle small changes of where your programming skills gets fine-tuned. So condensing these 3 lines to this 1 line with that little for loop indented within this function. As long as your indentation is all correct, you keep moving things in, you can output that list. And this whole stream was about efficiency and taking one program and becoming more and more efficient and proficient in what you're doing. So I think that's understandable. It's definitely there for those who want to see it. I'm just going to pop it onto group, and probably since this is the most successful one in 3 dimensions that has the shortest, most condensed script, we should make that blue. Let's thank Jake Hebbert and his online sources of visiting Nature of Code, which puts us back to Daniel Schiffman's work, and we just keep standing on the shoulders of all these wonderful giants before us as they go deeper and deeper into it, and into the past, and then what the future can be. So I'm just going to leave that, and maybe I'll just pop that to a nice big circle bouncing around for the end and make it blue. All right. Thank you very much for watching. Oh, I've left the page, but yeah, there it is. You get a little bit of kinetics going on with it, even doing the kangaroo app.